Okay, we're here for Video Lab Suite 16. It's number 16. And you are?
15. Audrey. Aisha. 10.
Okay, and who can tell us what's the lab all about?
Exothermic reactions.
And who can tell us what we mean by exothermic reactions? What's exothermic mean?
Doesn't require heat.
And what does it do?
It makes heat.
It makes heat, gives off heat, okay? And we have a chemical that we're going to use for that. Audrey, if you could tilt the beaker that you have there towards me so we can look into it. This is the chemical that's supposed to produce the heat for us. Kind of looks a little bit like Dippin' Dots, right? Who can give us the formula for the chemical that's in that beaker there?
CaCl2.
Yes, and who can give it to us in words? What does CaCl2 stand for?
Carbon chloride.
No, it's not carbon, Ca.
Calcium chloride.
Calcium chloride. And what elements make up calcium chloride?
Calcium chlorine.
Yes. Okay, so this is the chemical that's supposed to produce the heat energy, but it's not producing any heat energy now. What do we have to do to it to make it produce heat energy?
Add it to water.
Add it, say it again because somebody called.
Add it to water.
Yes, and how much water are we going to use today?
Me? 100 milliliters.
100 milliliters. All right, now we have a piece of equipment whose job it is to quantify the heat. In other words, to give it a number, okay? And what do we call the piece of equipment that's going to quantify the heat?
Thermometer.
Say it loud.
Thermometer.
A thermometer. You have to not move that stuff around, okay? It is easier to use on this side. It's okay. Okay, and Audrey, you have the thermometer. If you could hold it up and show the class. Okay, now in that thermometer, there is a red liquid. What do we call the red liquid in a thermometer? The red liquid. Yes. Hmm? No. Red liquid. Alcohol. And some thermometers have a silver liquid in it. And what do we call the silver liquid? Say it loud.
Mercury.
Okay, so this one has a particular one called alcohol. Now, let's see. When things get hot, what happens to the molecules when things get hot?
Speed up.
Okay, and when things cool down, what happens to the molecules?
Slow down.
They slow down. Now, we have different temperature scales whose job it is to quantify. All right, now, in this class, basically when you grew up, you were brought up on a particular temperature scale. And what do we call the temperature scale that you're used to?
Fahrenheit.
But you know that in this class, in science, we don't use Fahrenheit. What's the name of the temperature scale that we use?
Celsius.
Celsius. Now, there used to be a different name for Celsius. Before it became Celsius, it was
Centigrade.
centigrade, and they changed the name after the person who developed it. There's a third temperature scale. What's the third temperature scale?
Kelvin.
Kelvin. What do we use Kelvin for? I mean, we got two of them already.
Like really, really, really cold places.
And what's the advantage of using Kelvin over the other temperature scales?
There's no negative numbers.
Yes. The coldest temperature on the Kelvin scale has what number assigned to it?
0.
0, which is a positive number. Okay, now, there's a special name for 0 degrees Kelvin. What do we call 0 degrees Kelvin?
Absolute 0.
Yes. Now, you told me that when things heat up, molecules move quicker. When things cool down, they slow down. What happens at absolute 0 to the molecules?
You can't move or anything.
The molecules,
Go together and they stop moving.
they stop moving. Okay, the molecules at absolute 0 stop moving. Now, here's the first of the Doug questions. If you woke up one morning and outside it was absolute 0, and they told you the temperature on the radio in the Fahrenheit scale, the scale that you're used to, what would the temperature be?
170 degrees.
Nope.
Negative 273.
Nope, that is on the Celsius scale.
Oh, Fahrenheit?
We were looking for Fahrenheit.
Negative 470 degrees.
No.
You're close.
Negative 459.
Yes, very good. So we didn't have to play Prices Right under the first one. That's good. 459 degrees below 0 Fahrenheit is absolute 0. So if it was that cold that day, I would say probably don't go to school that day. Okay? All right, now, on each of these scales, whether it's Fahrenheit, Celsius, or Kelvin, when you're talking about water, there are things that are called fixed points, which are points of reference. There are 2 fixed points. They have a name in general, not a number, but a name. What's the name of one of the fixed points that we're interested in when we talk about water?
Boiling.
Boiling. And the other fixed point is?
Freezing.
Freezing. So now what I'm going to do is I'm going to give you a temperature scale. I'm going to ask you for one of the fixed points, and you're going to give me the number that goes with it. So kind of pay attention to what scale you're on. We'll start with the easy one, the one that you're used to, which is Fahrenheit. Okay? At what temperature on the Fahrenheit scale does water freeze?
32.
Yes. At what temperature does it boil?
210,
Close.
212,
212, okay? Let's go over to Celsius now. At what temperature does it freeze?
100,
No freezing, Celsius.
0,
0. And at what temperature does it boil? 100. Now we go to the Kelvin scale, the one for the low temperatures. What temperature does it freeze?
273,
Yes. And at what temperature does it boil? Say it loud.
373.
Very good. Now, there's no reason that we shouldn't win in this class. You've gotten through all the hard questions at this point. Okay, so we're kind of ready to get started. And you, Aisha, have a watch glass. We want you to weigh up the watch glass for us. And what'd you get?
81.7.
Okay, now if you would pass over your watch glass to Audrey, Audrey wants you to put a spoonful of the chemical into the watch glass. Okay, and then pass it back to Aisha. And Aisha, you're going to weigh it up a second time for us now. Did you get the number of that truck that ran over you?
Yep.
Okay. And what'd you get?
89.4.
Okay, now if she wanted to know what the contents of that container weighed, mathematically, what does she have to do? And that brings it over to Jen. So Jen, we want you to plug in those two numbers and tell us what is the difference of those two numbers.
7.7.
And if you could write down next to number of grams, 7.7. Okay. All right, now we said we needed some water. So Audrey, you're going to go up to the sink over there, take the thermometer out, put in 100 milliliters of water for us. Okay, now, I want you to put the thermometer into the water, and you're going to be taking a temperature in degrees Celsius that is called TI. What does TI stand for? Initial temperature, okay? And what does the word initial mean? What is it referring to here, if it was a vocabulary word? Initial.
First beginning.
Yes, what you're initiating it at, okay? So, Audrey, if you would read the thermometer for us and tell us, what does it say?
23,
23, and if you could put that down under the Celsius temperature. Now, if I wanted to change that Celsius temperature into Kelvin, mathematically, what do I have to do to make Kelvin? To add what?
273.
Say it loud.
Add 273.
Okay, and Jennifer, if you could take the number they just gave you, add 273 to it, and that'll be the Kelvin.
Equals 296.
296, if you can write that down next to K. Okay, now, let's see who's got what over here. Okay, Aisha, pass over your calcium chloride to Audrey. Audrey, you're going to dump the stuff into the water, and then you're going to stir it with the thermometer. Go for it. Making sure, of course, that you don't touch it with your hands because it's highly poisonous. Okay, now take a look at the thermometer right now, Audrey. What's happening to the alcohol in the thermometer? Say what?
It's going hot.
Use words. Say the words.
It's getting hotter.
It's getting higher, which means what? If it's getting higher, it means it's getting... It's rising, which means what about the water?
I said hotter.
Okay, say it louder.
Hotter.
Okay, so it's getting hotter. So this is the exothermic part of the reaction right now. Now, she's waiting for the temperature to get to something called TF. What does TF stand for?
Final temperature.
Okay, so what'd you get to?
32.
And if you would write down 32, and if you would plug in the 32, and tell us what's the Kelvin equivalent to 32.
305.
And if you could write down 305. Now, if we wanted to know how much did the temperature change during that time, Mathematically, what do we have to do? Yes. Subtract. And what is the mathematical symbol for the amount of change?
Triangle.
And if it was chemistry, what would the triangle be talking about?
Heat.
Okay, so if you would plug in the two numbers, Jen, and tell us how much did it change on the Celsius scale?
9.
And if 9, and if you put down 9 under the triangle, do the same thing for Kelvin for us. Plug the two numbers in. What's the difference of those two?
There is no difference in 5.
Hmm?
9.
9. Okay, and then if you could turn around what you've written, Chris will see the information that's here. All right, if you start with 7.7 grams of calcium chloride and you put them into 100 milliliters of water, the temperature both in Celsius and Kelvin will go up to be 9 degrees. So they both come up the same amount because they are both metric scales and they're based on the same sort of numbers, right? 9 degrees is a pretty big increase. Fahrenheit, it would be even more than 9 degrees. That's the temperature that you're used to. But it did go up to be 9 degrees. Now the question is, you had a hypothesis before you did this lab about how much you would drop into the water. If you dropped in more than the amount that they did. There were 3 possibilities that could have happened if you dropped a whole bunch of chemicals into the water. What was one of the possibilities? It would go lower. Maybe the more you added, there would be almost like a counteractive force. What's another possibility? It would get higher, okay? And what's the third possibility? Well, maybe it wouldn't have any effect on it at all. Now, what we did here is we took the 6 lab groups and we plotted their information on a graph. And Aisha has the graph. If you could hold it up and face the camera. So first of all, we're going to look at the picture on the graph, okay? And then we're going to see how did we graph it. On the x-axis, we were plotting the amount of grams of the substance that we were using. What do we call the variable that you plot on the x-axis? Say it loud.
Independent variable.
The independent variable. That's the variable that you as the experimenter control. Let's see the picture again. On the y-axis, we were plotting how much the temperature went up. And what type of a variable goes onto the y-axis? What do we call the variable?
Dependent.
Right, because it depends on what you did with the chemical. Now, when we did this experiment, there was a part of the experiment that didn't have any variable in it, which was called the control. What part of this experiment was the control? Had no variable associated.
The water.
The original water before we dropped the stuff in, okay? Let's look at the picture one more time. Okay, Aisha, I want you to show the class the actual graphing part so they can see how it came out. Show the class. Turn it around, show the class. People behind you as well. Now, is that a graph that is going up, going down, or staying the same? It's going up. What do we call a graph that goes up? What sort of a relationship is that called?
Direct.
A direct relationship. Very good. Now, if the graph went down, what would that be called? Indirect, but there's another word for indirect that also begins with IN. What's the other word, which is the opposite of direct, that begins with IN like indirect, but it... No,
Independent.
not independent. Inverse, very good. So when something is opposite of direct, that's inverse. Now that you've established that there is a direct relationship between how much of the material you use and how high the temperature gets. We're just coming out of winter now, right? What could you use this chemical for that has to do with winter?
Not the ice.
Yeah. How many of you have ever thrown salt on the ice? There's 2 types of salt that people throw out. They have a kind of a jagged sort of salt, which is called rock salt. And they have these Dippin' Dots that you throw out, which is calcium chloride. It melts the ice. When it comes in contact with water, it releases its energy in the form of heat, and that causes the ice to melt. Now that you know that there's a direct relationship, if you wanted to melt a lot of ice, based on this graph, what should you do? Yeah, use a lot of salt, because it's going to make a difference. All right? And that's what this whole lab is establishing for you.
Can you put that stuff in your pool?
Somebody said in the other class, they said, what could you use this for? And they said, to heat a pool. And I would say, no, that you shouldn't put it in your pool because it can react with you. This is not a good thing for, for your skin to react with. But that's what they thought it could be used for, heating a pool.